Hi, in this presentation we're going to talk about optimal path planning using RRT star based approaches, a survey and future directions. This is Sailesh Rajagopalan. Just to give you an introduction on what a paper here talks about path planning, we all know it is a collision-free path generation from an initial to a specified state with an optimal cost. Path planning algorithms are vital importance in many applications. Common applications include autonomous vehicle, UAV, forklifts for surveillance operations. At first, initial planners included roadmap potential fields and cell decomposition techniques. Talking about common grid search based, we have A star, D star, Jig star, and 5 star, which are complete but shortcomings of them are computationally expensive. There are other such particle spark optimization, bacterial foraging, and optimization of bioinspired neural networks, but are highly sensitive to search and space size. This paper includes major RRT methodologies and state if they are which are discussed in detail and methodologies behind them. This section introduces important path planning concepts related to RRT star in order to provide a better understanding of this study. It is essential to introduce the basic operations of RRT star prior to describing its variant approaches. These procedures are found in all RRT star variants, but their implementation may differ in different planners and applications. As you can see in image 1, is an RRT star expansion process. The tree expansion process in RRT star is by creating multiple short paths which are randomly organized as a tree instead of long paths. Starts at initial path, finds a path towards the goal. The configuration space it lies in the obstacles it is ignored by it. If the obstacle-free region, then its nearest node is defined. With the local planner, it connects the nearest and random ones by steering function. A Voronoi bias is what is called to ignore the free space, which is basically a collision check in process. If a collision is found, the neighbor with the least cost will become the parent and the new node is inserted as a child in the tree, and the costs are compared between them. The lower cost then rewiring builds the tree for a minimum parent in the area. In single directional RRT star generate path for holonomic robots by construction a single tree that starts from initial path to the goal state to find a path in the search space. In any time variant of RRT star, the idea is to deal with the large computation time space by executing the planner for a predefined planning time. Once an initial path is obtained and sorted, then rest of the time is used to improve initial solution. RRT star shortcomings include memory consumption due to the large expansion space, so more efficient. What is RRT star FN? Which allows limited number of trees. In an RRT star FN consumes a forcing a fixed number of trees in a node, as in when the global and local schemes are not when the node is not inserted. RRT star smart issues a slow convergence problems are addressed. Intelligent in sampling and path optimization, as one path is found is optimized based on triangular inequality. RRT star issues slow convergence problems are addressed in intelligent and sampling path optimization as well. RRT star sharp, RRT star smart, informed RRT star for optimal path planning in a narrow passage, and the methodology is direct subset sampling technique in configuration space within a limited elliptical area and are defined by ellipsoidal subsystem, improves rate of convergence and path quality. RRT star sharp addresses the issues slow convergence. Promising nodes are the ones which are good candidates to contribute in the final path with the lowest cost. During each iteration, RRT star sharp updates information about promising nodes and prioritize them for replanning in next iteration. Hence, it makes fast convergence by expanding promising nodes towards goal region and exploiting available node information to the highest degree at each iteration. Unlike single approaches, bidirectional approaches generate two trees simultaneously from start and goal states directing towards each other. RRT Connect is not asymptotically optimal like RRT star. Applying bidirectional trees to asymptotical optimal RRT star requires neighborhood rewiring in two trees, resulting in high computational costs. As asymptotic optimal variant RRT star and RRT Connect called bidirectional RRT. Though this procedure selects only promising nodes but also affects space exploration, moreover attempt to connect both trees in each iteration incur computational overhead. Optimal BRRT or BIRT is probably as asymptotic. Moreover, these biased heuristics infer with the algorithm characteristically optimal bidirectional approach with improved convergence rate using a number of heuristic techniques. It used an intelligent sample insertion heuristic technique. Simulation results of IB-RRT star showed fast convergence towards optimal path planning, less memory resources in comparison with RRT star and BIRT. Plan path from one topological space to another by human intervention. This approach addresses the planning problems of human-robot team interactions in search and rescue, police, and military operations. Effectiveness of proposed approach is theoretically proved using case studies. Kinodynamic planning refers to motion planning problems for which velocity and acceleration bounds must be satisfied. A car-like robot needs to change its position coordinates in order to rotate around its axis. It is underactuated due to non-holonomic constraints imposed by the wheels. Therefore, non-holonomic path planning requires satisfying both internal constraints and external constraints. Internal constraints include physical limitations of robot, external includes obstacle in environment. Moving on to discussing on what we can see. SRT Star has fixed the planning fixed wing UAV in 3D environment. The use of Bezier spline parameterization and SRT Star as a local planner replaced time and input discretization. Moreover, it performed dynamic feasibility and geometric collision checks as part of the tree expansion. This phenomenon enabled SRT Star to produce smooth and cost-optimal path in 3D simulations using constraint model of UAV. RT star I is for efficient motion planning, so UAV it computes a more predictable and smoother trajectories compared to RRT or RRT star methodology. Behind it is, after it finds the trajectory, it adapts local sampling by Gaussian distribution and node rejection technique. Doing such techniques, it has the ability to define tree in vicinity of initial path solutions. RTR plus CS sharp uses a global and local planner defined for car-like robots. The global planner is called rotate, translate, rotate, or RTR for path generation. The local planner is C-sharp CS, which is done by using circular arc and straight segments. DTRRT manages two trees called state and workspace. Workspace explores targeted environment without the considering of any physical constraint, wherein state tree generates trajectories similar to Rewire and RRT star. This has a reconnect tree, maintains child nodes, and reduces computational cost. This scheme has positive in reducing space dimensionality, as IR reduced the node rejection chances by applying kinodynamic constraints. Mitsubishi RRT Star proposed an approach that used the two-state sampling strategy similar to SRRT. This is specifically for autonomous vehicles. Implied two-phase surfaces meet along a common edge tangent, and the rate of curvature change at each point along the edge is equal for both faces and surfaces. A local replanning procedure enables algorithm to react with dynamic obstacles. CA-RRT star, cost-aware RRT star, is for an energy-efficient optimal path planning in a high-dimensional space, but is limited to only humanoid robots as its shortcomings. The ideology behind it is if the first tree is extended as an standard RRT star to determine the nearest node to new sample random points. Also, a cross-entropy path planning and a cost function based on mechanical work was introduced to measure the energy consumption for humanoid. Transition-based RRT star focuses more on optimal path planning for continuous configuration cost space. The approach integrated multiple transition-based function to address the issue of path planning, path quality with respect to a given criteria. RABIT star is a relatively new introduction proposed method that focuses on homotopy class, which are difficult to sample for narrow passages. It extended by an informed global technique called BIT star by using a local optimization module to improve an initial suboptimal path towards local optimum. This slide is just a summary of the overall methods we have explored in the previous slide with constraints and type planning, kinematic model, and the sampling strategy we need. For improvements on state-of-the-art methods we have explored, we face limitations in various phases, but these are prospective challenges. Slow convergence and small large memory requirements, we can clearly see that there are shortcomings in RRT. One way to explore that works has been done by the search space using different sampling strategies like goal-biased and direct or intelligent, as we can see in the image here. However, these solutions are only explorational. They require a good balance of exploration and exploitation in search space. Dealing with narrow passages in uniform sampling of RRT star reduces the probability of node selection to address this problem specifically. Informed RRT star by heuristic dependent on initial solution. HAART star does thus exist to achieve optimization and reliability, but it's experimental. In kinodynamic constraint, the concept of dealing with narrow passages is still a research question. With respect to efficient of the nearest neighbor search, as trees expand exponentially, it is hard to maintain a method to efficient by fixing maximum possible nodes in a tree can be used. In KD tree space and neural network search for Euclidean space too. Other methods can significantly increase costs. With post-processing requirements, two common types of pruning, both local and global, are shown. In case of UAV and car-like robots, pruning generates linear-wise, piecewise function, which is not feasible in them. To resolve this, in RRT star variants discussed above, the spline methodology using Bezier was discussed, but these have limitations too of maintaining continuity using a suitable degree of curve. In non-holonomic and kinodynamic constraints after trajectory generation, complexity of planning of search space is expensive. Dealing with kinodynamic complexities, considering the robot's orientation to state vector increases complexity of the configuration space, making it challenging for motion planning RRT star applications. With non-holonomic motion requires more iterations. to converge than a holonomic version. Usually, path planners generate linear piecewise path, ignoring all kinodynamic constraints, and path smoothing is applied later as post-processing step, as discussed above. Recent state of the art is inclined to apply kinematic constraint model while searching the path to avoid complexities in post-processing. Conclusion: traditional path planning are not feasible for non-holonomic situations. RRT style is the best complex problem as we've seen from comparing all the things that we've talked about. Kinodynamic constraint issues of high dimension, narrow passage, and peak of accuracy and efficiency, as we can see. This slide is just a reference of what the paper that we have worked on.